Look at the two images. The first one shows air particles in random motion, air molecules in random motion around a block. This is what what a block just sitting in a room in a regular environment might look like. All the If you remember from previous science classes, you know that gas molecules move randomly. So if you have a bunch of gas particles, air particles, air molecules moving randomly around an object, then they're going to be pushing it from every direction. That's what we know as air pressure. Now, what if you could direct the air molecules to move in one direction? If you could change that from random motion, where they're all hitting it from every side, if you could create organized motion, where all the molecules hit the block from the same side, if you could get all the air molecules to hit the block from one side, moving the same direction, you would get a lot of force out of them. And that would be more useful for transferring mechanical energy to the block, because they would all in the first image they're all hitting it from random directions, so they're applying roughly an equal amount of force from every direction. In the second image, in organized motion, they're all pushing together, they're all pushing in the same direction. So if you could get the air molecules to do this, then you could get the air molecules to apply a force to a block in one specific direction. When we discuss energy, it's often appropriate to describe it in terms of utility or usefulness. This is important because different types of energy may be useful or not, depending on the context. For example, in a car engine, thermal energy is an unwanted byproduct, right? We want the energy in a car to be converted from chemical energy. We want as much of it as possible to be converted to kinetic energy. But let's say you have a heater that is made to generate heat. Well, then the heat is not a byproduct; it's actually the wanted product. So sometimes mechanical energy is what we want. Sometimes non-mechanical energy is what we want. If we concentrate non-mechanical energy in one place, or mechanical energy, if we focus it in one direction, then that tends to be more useful than unorganized energy. In these images showing particle motion, the both of the blocks are surrounded by the same number of particles. Each particle has the same amount of kinetic energy, or rather, there's the same amount of total kinetic energy, the same average amount of kinetic energy per particle, otherwise known as temperature. So the gas is the same temperature, but we can see that the second block is more likely to move. The first block will stay in place because it's being pushed from every direction. The particles with organized motion are moving toward the block from the right to the left. Their energy is concentrated in one direction, meaning that that block is much more likely to move. Organized energy like this moves something in a predictable way. Unorganized energy spreads out in different directions and is not as useful to us. Unorganized energy is typically transferred to the surrounding environment. This is a diagram of a system. It's a model of a system, and the system is what we define it. Systems have boundaries that define their extent. We define what system we're going to be studying. The boundaries can be real or they can be hypothetical depending on the system. If you talk about a car engine has cylinders that move up and down because of the combustion of fuel. And even though the engine is a much larger machine, you can define the boundary of the system as the walls of the cylinder, because that's where the combustion takes place. So you can study just what's happening inside the cylinder, and in that case, the cylinders are real physical boundaries for the expanding gas. That's a useful model because we want to measure how much of the energy inside the cylinder is useful. It moves the cylinder up and down, and how much of it is wasted. We don't we don't necessarily care if we're just studying the motion of the engine. We don't necessarily care where the energy is wasted, where the energy, the non-mechanical energy goes to. Some of it can go to the block, the engine block. Some of it can go to the environment. Some of it can be absorbed by the actual piston. We just want to know how much. If we just want to know how much of it is useful, then we define the system in a way that meets our needs. So systems have boundaries. They can be real or imaginary, hypothetical, and it depends on what you are going to be studying. If so, here's an actual image of an engine. So an engine, if you we look at an engine from the right angle, we can see that it has several cylinders, and from one angle, this engine has one cylinder. Okay, so we're defining the cylinder is the space. It's this structure here. Okay, so the cylinder is a cylinder shaped structure, and then inside the cylinder you have this object called the piston, and the piston moves up and down because of combustion that takes place inside the cylinder. So little explosions inside the cylinder push the piston up, and then it come or in this case push the piston down, and then the piston comes back up. Then there's another little explosion. The piston goes down, and so this happens very fast and very often. And so we have the piston going down, up, down, up, down, up, down, up, down, up, down, up, down, up. And each time there's a little explosion inside the cylinder, and fuel is burned. Now, in the first engine, in the first image, we see most of the thermal energy within the engine cylinder. So we don't have a lot of thermal energy escaping. We don't have a lot of heat transferring outside the cylinder, and so that is organized thermal energy. On the second picture, we see diffuse thermal energy. That's where we lose a lot of heat, or that's how we would say it. We lose a lot of heat, or there's a lot of thermal energy that gets spread throughout the system. Energy tends to be considered useful when it's organized in such a way that it can make something move in a predictable way. In this first image, we can make the piston move in a predictable way. In the second image of diffuse thermal energy, we're, we can still get the piston to move in a predictable way, but we're not using as much of the available energy to make it happen. There's more non-mechanical energy. So there's non-mechanical energy spread throughout the system, or actually leaving the system if our system is the cylinder. So the um, the first image is much more useful because we have non-mechanical energy concentrated in one place, and then that creates mechanical energy that is focused in one direction. That non-mechanical energy in one place can push the piston down. Like, that causes mechanical energy focused in one direction, rather than the second image where we see a lot of non-mechanical energy spread out, and we also see that the mechanical energy is going in every direction. It's not just pushing the piston down; it's pushing the cylinder out in every direction.